our last lab, we explored the science of meteorology. We performed a weather analysis and even tried a little weather forecasting. In this lab, we will discuss the kinetic-molecular theory and demonstrate two of the gas laws dealing with the pressure, temperature, and volume of a gas. As always, before beginning any experiment in the laboratory, be sure you are familiar with laboratory safety requirements. For a demonstration of basic lab safety rules, you can watch our video entitled Lab Safety. Because particles of matter are so tiny, we cannot directly observe how they interact. However, scientists have developed a theory to explain how particles behave. This theory is called the kinetic-molecular theory of matter. According to the kinetic-molecular theory of matter, all matter is composed of tiny particles such as atoms, molecules, or ions, and these particles are in constant motion. This theory applies to solids, liquids, and gases, but its effects are best observed in gases. Let's consider a 1-liter sample of oxygen gas. At standard temperature and pressure, 1 liter of oxygen gas contains approximately 2.7 times 10 to the 22nd power molecules. Each molecule is made up of 2 oxygen atoms. Oxygen molecules are constantly moving in random, straight-line paths, colliding with each other and with the sides of their container. These collisions are called elastic collisions because the particles do not lose energy when they collide. Usually, when 2 objects collide, some energy is lost. Because of this energy loss, moving objects that collide will eventually slow down and come to a stop. However, gas particles do not lose energy when they collide, so they continue moving. By applying the kinetic-molecular theory to the motion and collision of gas particles in a closed container, we can account for 3 important properties of gas particles: pressure, volume, and temperature. When gas particles collide, they produce a force called pressure. Pressure is defined as the amount of force being applied to a unit of area. In terms of gas particles, pressure describes how hard the gas particles push against themselves and against the walls of their container. The second property of gas molecules is volume, which is the amount of space occupied by an object. Because gas particles collide with each other, they spread out and evenly fill whatever container is holding them. Because of the motion of particles in any substance, matter contains kinetic energy. The total kinetic energy of a substance is called heat. However, particles do not all move at the same speed, so the amount of heat in a substance varies from place to place within that substance. For that reason, scientists often refer to the average kinetic energy of a substance. The average kinetic energy of a substance is called temperature, which is the third property of a gas. After many years of research and experimentation, scientists discovered that the pressure, volume, and temperature of a gas are related, and that a change in one property affects the others. The relationships between these properties are summarized in the gas laws. One gas law states that the volume of a gas is inversely proportional to its pressure if the temperature remains constant. This law is sometimes called Boyle's law, named for Robert Boyle, the 17th century Irish chemist who discovered the relationship. Using the letter P for pressure and V for volume, Boyle's law can be expressed mathematically as P is inversely proportional to V. In situations involving a change in volume or pressure, Boyle's law can be expressed as an equation. if we use P1 for the original pressure, P2 for the new pressure, V1 for the original volume, and V2 for the new volume, Boyle's law can be expressed as P1 times V1 is equal to P2 times V2. Let's look at an example using the equation for Boyle's law to see how volume and pressure are inversely proportional. For this example, we will measure pressure in atmospheres. 1 atmosphere of pressure is equal to the pressure of air at sea level at a temperature of 0 degrees Celsius. Volume will be measured in liters. The pressure in our example is 1 atmosphere and the volume is 4 liters. The temperature will remain the same. Next, we reduce the volume to 2 liters. What will the new pressure be? The volume decreased from 4 liters to 2 liters. Since volume and pressure are inversely proportional, the pressure will increase when the volume decreases. So, what will the new pressure be? To find the new pressure, we use the equation for Boyle's law. We can calculate the unknown value if we know the other 3 values. In this example, we are given the original pressure, original volume, and new volume. We can use the equation to calculate the new pressure. Since we are solving for P2, we rearrange the variables of the equation and substitute the given values. Notice that the units for volume cancel and only the unit for pressure remains. After we solve the equation, we arrive at an answer of 2 atmospheres. Is this a reasonable solution? The given volume decreased by a factor of 2, and the pressure increased by the same factor. Therefore, this is a reasonable solution. Boyle's law can be explained using the kinetic-molecular theory. This container of gas has a volume of 4 liters. The collisions of the particles in the container exert a pressure of 1 atmosphere. For Boyle's law to work, the temperature of the gas must remain constant. If the volume of the gas is reduced to 2 liters by depressing the plunger, the particles are squeezed into a smaller space. Since the particles are closer together, the number of collisions increases. As a result, the pressure increases to 2 atmospheres. To demonstrate that the pressure and volume of a gas are inversely proportional, we can use an instrument called a U-tube manometer. A U-tube manometer is a clear glass or plastic tube that is bent in the shape of a U and partially filled with red indicator fluid. Right now, the tube is open at each end at the top of the U. When the ends of the tube are open, atmospheric pressure presses down equally on the indicator fluid in both sides of the tube. If a gas under pressure is connected to the left side of the manometer tube, the manometer can detect changes in the pressure of the gas. The manometer measures a change in pressure with a scale attached to the tube of the manometer. What do we mean when we say the manometer measures a change in pressure? Instead of measuring the actual pressure, a manometer measures how much the pressure of a gas increases or decreases. If the pressure of the gas connected to the manometer is equal to atmospheric pressure, the level of the indicator fluid will be the same in both sides of the tube. If the pressure of the gas on the left side of the tube is less than atmospheric pressure, the level of the indicator fluid will rise on the left and drop on the right. If the pressure of the gas on the left side of the tube is greater than atmospheric pressure, the level of indicator fluid on the left will drop and the level on the right will rise. If it seems strange that an increase in pressure makes the fluid level drop, remember this. If the pressure of the fluid increases, then the molecules of the gas are pushing down harder on the surface of the indicator fluid, which forces the fluid level down. If the pressure of the fluid decreases, then the molecules of the gas do not push down as hard on the surface of the indicator fluid, which allows the fluid level to rise. If we know the original pressure and we know the change in pressure, we can add the amount of the change to the original pressure to find the new pressure. For instance, if the original pressure was 1 atmosphere, and we can use the manometer to determine that the pressure increases by 0.2 atmospheres, we can calculate the new pressure by adding the two values. The new pressure is 1.2 atmospheres. What happens if the pressure decreases? A decrease in pressure is a negative change. So, if the original pressure was 1 atmosphere and the pressure decreased by 0.2 atmospheres, we know that the new pressure is 0.8 atmospheres. To test the proportional relationship between the volume and the pressure of a gas, we have connected the left side of the manometer tube to a flexible tube, which contains 60 milliliters of air. The tube is connected to a large syringe. The plunger on the syringe is pulled out to the 30 milliliter mark. So, the total volume of air in the syringe and the tubing is 90 milliliters. This is the original volume, or V1. The fluid levels on both sides of the manometer are at the 0 mark. This indicates that the original pressure of the trapped air, or P1, is 1 atmosphere. Now we will increase the volume of air on the left side of the manometer. By pulling the plunger back to the 40 milliliter mark, we have increased the volume by 10 milliliters. This gives us a new volume, or V2, of 100 milliliters. Since the volume increased, what should happen to the pressure of the air on the left side of the manometer? According to Boyle's law, pressure and volume are inversely proportional. So, if the volume increases, the pressure should decrease proportionally. A decrease in pressure would cause a rise in the level of the fluid indicator on the left side of the manometer and a drop in the level on the right side. But was the decrease in pressure proportional to the increase in volume? To determine if the decrease in pressure was proportional to the increase in volume, we need to know how to calculate the amount of change in the manometer readings. The scale on the manometer is marked in millimeters. The fluid level on the left side of the manometer rose to the 150 millimeter mark above 0. At the same time, the fluid level dropped on the right side to the 150 millimeter mark below 0. This was a total change of 300 millimeters. A change of 300 millimeters of the fluid levels indicates a change in pressure of 0.1 atmospheres. Since the pressure decreased, this indicates a 0.1 atmosphere drop in pressure. So, the new pressure, P2, would be 0.9 atmospheres. Let's see if the change in pressure indicated by the manometer matches what we would determine using the equation for Boyle's law. We begin with a pressure of 1 atmosphere and a volume of 90 milliliters. What would the new pressure be if the volume changed to 100 milliliters? If we start with the equation for Boyle's law and rearrange the variables to solve for P2, we see that the new pressure is 0.9 atmospheres, which is consistent with the reading on the manometer. The volume increased by a factor of 1.11. and the pressure decreased by a factor of 1.11. So our readings confirm Boyle's law. When we return the volume to its original value of 90 milliliters, the pressure also returns to its original pressure of 1 atmosphere. Now, let's decrease the volume and see what happens to the pressure. We push the plunger of the syringe into the 20 milliliter mark. This gives us a new volume of 80 milliliters. Let's see what happens to the pressure reading on our manometer. Notice that the fluid level on the left has dropped to 150 millimeters below zero, and the level on the right has risen to 150 millimeters above zero. This is a change of fluid levels of 300 millimeters, which indicates a pressure change of 0.1 atmospheres. The change in pressure is 0.1 atmospheres, the same as before, but this time the pressure increased. The new pressure, P2, is 1.1 atmospheres. Is this reading consistent with Boyle's law? Let's find out by applying the Boyle's law equation. The pressure increased, and the volume decreased proportionally. Once again, our readings confirm Boyle's law. We have been looking at applications of Boyle's law, which involves the pressure and volume of a gas. Another gas law, called Charles' law, involves the temperature and volume of a gas. In the late 1780s, a French physicist named Jacques Charles was experimenting with hydrogen-filled balloons. He discovered that a change in the temperature of a gas caused a proportional change in its volume. His discovery became known as Charles' law, which states that the volume of a gas is directly proportional to its Kelvin temperature if the pressure remains constant. Notice that Charles' law mentions Kelvin temperature. The relationship between the temperature and volume of a gas is proportional only if Kelvin temperatures are used. Kelvin and Celsius temperatures rise and fall at the same rate. So, to convert a Celsius temperature to Kelvin, add 273 to the Celsius temperature. For example, if we have a temperature of 22 degrees Celsius, we can change it to Kelvin by adding 273 to the Celsius temperature. Temperatures in Kelvin do not use the degree symbol. Using the letter V for volume and T for temperature, Charles' law can be expressed mathematically as V is directly proportional to T. Because this is a direct relationship, a change in the Kelvin temperature of an enclosed gas will produce a proportional change in the volume of the gas. We can demonstrate this relationship between the volume and temperature of a gas with these three syringes, which are marked in 0.2 milliliter increments. Each syringe has been capped, so it contains exactly 5 milliliters of air at room temperature. The temperature of the room is 293.9 Kelvin, or 20.9 degrees Celsius. We also have 3 beakers of water. The first beaker contains water, ice, and salt to lower the temperature to 273 Kelvin, or 0 degrees Celsius. The second beaker contains water at room temperature, or 293.9 Kelvin. The third beaker contains water heated to 373 Kelvin, or 100 degrees Celsius. We will see how changing the temperature affects the volume of air trapped in each syringe if the pressure remains constant. The syringes must remain in the beakers for 5 minutes until the temperature of the air in each syringe matches the temperature of the water in that beaker. While we wait for the temperatures to change in the syringes, let's discuss the equation for Charles' law. If the volume and temperature of a gas change, but the pressure remains constant, the equation for Charles' law can be used to calculate the new volume. With V1 for the original volume, T1 for the original temperature, V2 for the new volume, and T2 for the new temperature, the equation is expressed as V1 over T1 is equal to V2 over T2. The temperatures must be expressed in Kelvin for calculations. Let's check each syringe to see how the volume was affected by the change in temperature. The temperature in the first syringe decreased from 20.9 degrees Celsius, which is 293.9 Kelvin, to 0 degrees Celsius, which is 273 Kelvin. The volume of air trapped in the syringe decreased from 5.0 milliliters to 4.6 milliliters. Both the temperature and volume decreased by a factor of 1.08. Let's look at the second syringe. The temperature of this syringe did not change. The volume also did not change. The temperature in the third syringe changed from 20.9 degrees Celsius, which is 293.9 Kelvin, to 100 degrees Celsius, which is 373 Kelvin. The volume of air trapped in the syringe changed from 5.0 milliliters to 6.4 milliliters. The temperature and the volume increased by the same factor, 1.27. By using a manometer and some syringes, we have demonstrated the validity of both Boyle's law and Charles' law. In our next lab, we will demonstrate some of the basic types of chemical reactions. At this time, proceed with the corresponding activities.